Executive. Dr. Yiming Huo, he received his undergraduate degree in information engineering from Southeast University in 2006, and then MSc MSc degree from Lund University in 2010, and PhD from the University of Victoria in 2017, where he's currently a research fellow. And he has worked with several organizations and institutes, including Ericsson, ST Ericsson, ST Microelectronics, Apple, and is a recipient of several awards, including the most popular article of IEEE Access. And his work has been cited in World Economic Forum and featured in the Forbes magazine. He's a very active member of the Massive MIMO working group and has been involved in several IEEE activities. With that, the floor is yours, Dr. Huo.
Okay, thank you so much, Kuma, for your introduction. So I think everybody can see my screen, right? So I'm just doing the slide showing. So can see my full screen, right? Okay. So here comes today's topic: enabling a more prosperous space Europe, a massive MIMO perspective. So good morning, afternoon, and evening. How's everyone been doing? What a big honor and pleasure to be here to share and exchange thoughts and ideas with communities, colleagues, and fellows from all over the world. All right, so here comes the outline of today's topic. Basically, we have two major topics here. The first one, space broadband access. The race has just begun. And the second one, massive sensing, communication, and defense in space, which is literally a matter of life or death. So, we know that the space broadband access is a huge and hot topic in recent years. And what do you guys immediately think of? NASA, SpaceX, Starlink, Blue Origin, or Rocket Lab, etc., etc. So we have so many very visible players in the in this area recently. And why is that? Okay, first of all, I'd like to say the space broadband access is a very critical component for the 5G and beyond, and even 6G ecosystem is a long term. So from this year and beyond will be the time of technological singularity, when significantly more LEO satellites are to be launched, deployed, and planned. There was a temporary recession, as you guys remember, several decades ago. We have the Iridium system, which is not so successful, but it gave a very good demo. It's due to maybe immature business model, affordable cost, and other technical challenges, which have been alleviated a lot today. So, today's ISP, Internet Service Provider, always targeted connecting the unconnected. So the long terrestrial wireless communication, including such as UAV communication, high altitude platform, HAB communication provides a complementary and a compatible solution. LEO satellite mega constellation can provide very wide coverage and the constant broadband access services in rural areas, remote areas, and mountainous areas, as shown in Figure 1, the Alps and mountainous areas, as you can see there. There's a very lively town there, but you have to give the coverage and service there. And also maritime communication, right? Like a deep sea, where you basically don't have any infrastructure today. So you have to rely on the telecommunication. So space broadband access can robustly cope with terrestrial emergencies such as earthquakes, hurricane, forest fire, etc., etc. So what does this space industry suddenly just catch our attention just in recent years becomes really booming exponentially? There is something called Watt's law, which is originally from the Theodore P. Watt, which is who is an aerospace engineer and educator, as you can see the formula here. So basically, compared to the Moore's law, Watt's law offers better prediction for like battery, like a lithium battery and auto industry for very long time, over a century. So it can be applied to satellite bandwidth according to Art Invest research since 2004. The cost has dropped by more than 7,000-fold from 700 million US dollars per Gbps to only 40K, and it could fall another 40-fold during the next 5 years, which is so amazing. So you can see the plot I give here about the real launch cost over the time from like 1990s until like 2020s, and hopefully with like more advanced launching vehicles like Starlink, we can achieve like even lower cost. Okay, so here comes summary about Starlink satellite launch information monthly basis, which is really amazing, right? You can see the momentum here. And also, I has to quote the Art Invest research again. As you can see, satellite bandwidth cost decline really exponentially. Okay, then it can enable a lot of new services, vertical applications. So the state of the art, so on constellations, Starlink, OneWeb, Telesat, Amazon Project Cooper, and Boeing. They have good planning or already got the deployment, but obviously Starlink leads in this area. So here comes the frequency and the channelization plan of Starlink system. So it's a little bit complicated because you have the user downlink, gateway downlink, user uplink, gateway uplink, and telemetry control stuff. And so for the G1, usually below 30 gigahertz. But for the G2, it was it's notable that we're gonna use like V band here. Gonna be really, really high frequencies there. So G2, we're add more Q and K band. And G2, we're deploying more NEO satellites there, and we'll achieve 10 times the total throughput as the G1. And very important here, because from previous talk, Dr. Ning mentioned about artificial intelligence important role. Of course, for the satellites and the space broadband, you have to put the artificial intelligence cloud edge computing system. Starlink already has started the collaboration with Microsoft and Google, right? Okay, so here comes the illustration of real-time orbital and location information. So this is Starlink. This is OneWeb. So OneWeb got their satellites a little bit further away from the Earth's surface, like using possibly 1,200 or 100 something kilometers as their orbital altitude. So let's do some like big picture review here. Recent and future trends of the near Earth space communication. So LES definition is like it's the area from the layers of neutral terrestrial atmosphere up to the lunar orbit. So basically, the moon is still within our near Earth space. And the SpaceX and the T-Mobile announced, as you guys know, like August 25, collaborating on using mid-band PCS 1.9 gigahertz directly to mobile devices in next year. So Mr. Elon Musk mentioned that we're gonna deploy larger NEO satellites since you have to give very large antenna or antenna arrays there. Then from last month, like Apple announced that released the iPhone 14 models, which support emergency SOS services via global stars satellite services. So I think that can be a very good trend, and lots of corporations gonna follow up, I think. Then, but we also can see that like there could be a deeper integration with terrestrial communications, like I mentioned earlier, like UAV and HEP communications, and also not necessarily limited about the terrestrial. So it's gonna be to the moon, since Artemis plan gonna build up the permanent base there. So we know that Nokia Bell Labs gonna build up the first LTE networks. All right, so there are gonna be serious challenges, but also promising opportunities, of course. Then the first challenge is like the coexistence and integration, and how could we mitigate the inter-constellation interference, right? For example, between Starlink and OneWeb, since Starlink use like a lower altitude and OneWeb stands a bit higher, then there could be possible some interference, and also like inter-facilities, which I mean between neo satellites and also terrestrial interference. Or therefore, the beam management, spectrum management are very important here. Also, another challenge, and we heard a lot of complaints from the NASA International Space Station and also ESA, etc., about reporting the junk collision in the space, as you can see here. So I suppose the regulations and also like techniques for collision avoiding and safe deorbiting very critical here. So and also I suppose fast satellite movement introduced very severe Doppler effect. So it's attitude dependent. Frequent handovers and complicated beam alignment and management. So more systematic optimization will be required for the performance, since the customer user experience really care about the latency, about the throughput. With that being said, handling extreme weather conditions is another serious mission. So you possibly need better hardwares like histories and signaling algorithms, like AI-assisted wireless communications, cloud and edge-assisted data computation uploading could be also very important here. So, but it's really promising because according to some analysts from Citigroup, the space industry should achieve 1 trillion in annual revenue by 2040. Okay, so by wrapping up this section, I go to the second major topic here. So massive sensing, communication, defense in space. So this is a little bit futuristic, but it's still very practical, I gotta say. So here. So first of all, I'd like to quote Dr. Carl Sagan here. The cosmos is also using ours. We are made of star stuff. We are way for the cosmos to know itself. So I bet most of the people here very excited about the first images from James Webb Space Telescope. So curiosity and courage have been motivating us to explore the broad universe and unveil many mysteries of it. So a historic milestone was marked on July 12, when the first full color image from GWST were released to unfold the infrared universe. This symbolized the dawn of a new era in astronomy. But actually, it's not only about curiosity and courage. It's also about the life or death. Why is that? Because there are serious threats from the space. It's just a matter of time, in my opinion. So we know the KPG extinction events, which caused us, Chicxulub crater in the Gulf of Mexico, Yucatan Peninsula, 6 million years ago. And we have the evidence from younger dryas event, like more than 12,000 years ago. And in last century, we have the Tunguska event, right, which is very serious and still mysterious. And last decade, like almost 10 years ago, we have Chelyabinsk event. Unfortunately, we have no warning because no alarm was triggered ahead because that meteor was in a region of the sky giving no access to ground-based telescopes. So, so I give the comparison here about the approximate size of 3 notable impactors with New York Manhattan as a background here. So Chelyabinsk, Barringer's crater, and the Tunguska. Okay, so we can have some like inspirations from like Earth's life evolution, like around 500 million years ago, sea creatures likely related to arthropods thus began making forays onto land, possibly to escape hungers and competitions to obtain better survival chance, right? Then prepare for the terrestrial transformations, develop this massive increase in the visual range, basically like visual sensing. So for terrestrial vertebrates, large eyes appeared from terrestrialization. There was actually very solid evidence and study here. So from like I think from like a penis, this journal, PNAS journal. So as you can see, how the life developed the vision from the water and then shallow water and eventually underground. So huge questions here could be, what about mankind's, what about mankind's sensing and communication capability enhanced by various technologies today? Where our enhanced capability lead us to, and how we are use this capability to serve better entire humanity, our planet, right? So it's making humans multiplanetary species. I think it's could be mandatory because if you look at the time domain from evolution of the terrestrial vertebrates here, like more than 300 million years ago, and then follow that, first the dinosaurs appeared on Earth. Another 160 million years passed, then dinosaurs encountered this KBG extinction event and got themselves totally wiped out from the Earth. And present day Homo sapiens with enhanced sex capabilities and aerospace and the various other technologies. What should we do with that? From terrestrialization to extraterrestrialization, that's one of my huge questions here. So when the civilization levels, I suppose, reach some threshold, it is both spontaneously and mandatory for space to leave its planet of origin, and it becomes multi-planetary. So terraforming, and also from Elon Musk papers concept about how to do the Mars transit system. And possibly someday we could build up the Mars city for the permanent surface base, not only in the cave or tunnels on Mars. And also we can look a bit further into other solar systems like exoplanets becomes a very hard research in recent years. For example, the Kepler 22b is supposed to be very similar planet like Earth and in the habitable zone in the Kepler 22 system here. All right, but it's a little bit further away, 629 years from us. But in the meantime, we humanity also set up the planetary defense, like planetary defense coordination office (PDOC). I think is set up since 2016, and we have to know where our risk or enemies from. You know, those near Earth objects or asteroids. They're from either the main asteroid belt between the Jupiter and Mars, and also like somewhere else even further away from like Neptune or Uranus, like the Kuiper belt here. So this is the survey from the PDOC and near Earth asteroid discovered over the time, you know, more and more here. And the size over 140 meters can be very deadly. Can easily wipe out one nation or something. Then this is a categorization by different service stations, like some stations on ground, some station in the space, as you know here. Then four types of NEO, known as HI-18, Apollo, and AMO. So it depends on their orbit. And also this show how to survey, track, and as NEO. Like they have very complicated orbits here, but we have the mitigation technologies, as I mentioned, like as we guys as we know that like DART was very successful, like just 1 week ago. This successfully launched from Falcon 9, and the got the successful impact on the move of the Didymos here. So hopefully, sometime later we can see the change of the orbit, and so you can see the illustration of the DART mission at the scale here. This is where impact happened for the DART, and this is from the Hubble and GWST's images. So other mitigation technologies here, it could be like a gravity tractor, like over the focus solar energy, but this year stay in the series, not yet fully tested. All right, but nuclear explosion device, there could be some very serious concerns here, like NPT, like also some research unveiled that actually it cannot effectively demolish the threat, because basically some asteroid is like a pile of loosey rocks, and if you separate them by the explosion, and then they come all together again by the gravity. So in my research, I proposed something called the Solo Communication and Defense Network, or SkyBeam, to enable massive sensing and communication in deep space. Basically, we're gonna deploy a large number of spacecraft service stations. They can be in visible light, millimeter wave terahertz, infrared, X-ray, multi-sensing capabilities, and we send them to the lock-down point of each planet. Since lock-down points can give them the best energy efficiency, and then you do the massive sensing with high spatial diversity. So the situation of the trade-off basically will be largely reduced or mitigated, because you have the sensing from all types of aspects or angles. Then you can give you better chance of early detection and mitigation successful. Because if we, for example, this is the Jupiter's orbit, and if we find some like risky object there, and you can do the early detection, and you can do the early interception, or like a mitigation or deflection. Yeah. So, but consider the huge distances, among planets and spacecraft. artificial intelligence and space-based edge and cloud computing, machine learning, such as federated learning, could be so important here. And they can enable the fully autonomous detection and mitigation and reduce the manual errors and latency. Because there's a large latency between the Earth and the Jupiter, or Saturn, or even further space. All right, then here comes some opportunities and challenges: physical limitation, propagation loss, and speed of light, latency. And Moore's law and Watt's law are co-enabling an enormous internet of spacecraft across solar system. Long-term universal efforts led by multiple organizations, governments, corporations, universities, research institutes. Very rigorous legalization and supervision should be required, considering the NPD and also Outer Space Treaty. And other unexpected disruptive factors to the supply chain could be one of the challenges. Because it leads a lot of vendors and efforts to build, maybe hundreds or thousands of spacecraft or space stations. But it's a very beneficiary for the ultimate benefit of mankind. So here comes some comparison of the parameters for different planets here. So I give the distance. I also give the free space path loss here. And also the latency. Latency here is really large, like 8 minutes for the Saturn. But Voyager 1, which has already become interstellar spacecraft, and it has more than 300 path loss. So how to close the Earth link, which could be a very serious challenge for the future deep space communications. All right, so then I will give the summary here. A more prosperous and diverse space era is unfolding in front of us. Many catalysts in our civilization have accelerated its arrival at us. Space technology and massive MIMO sensing communication capabilities are reshaping really fast our civilization. It's not only bring us the research and commercial opportunities, but also bring more fundamental but more critical concerns to us. First one, where will humanity go with these technologies? Will become multiplanetary be sufficient to solving all the problems on the Earth? How will humanity use them to better optimize its long-term evolution, LTE, of humanity? So that's my presentation. Thank you for your attention.
Thank you, Dr. Ho. Very exciting presentation and really nice information to learn on the interplanetary networks. So we do have some time for questions, and audience members are welcome to type in their questions in the Q&A. In the meantime, just to take this conversation forward and about the article in the Forbes magazine about your paper, I was just wondering that once we have this huge network in space, already there is an issue of space debris and a lot of pollution of space debris around the planet. And now with this proposed interplanetary network, we will have even more nodes. So what is your take on that?
So you mean could you rephrase your question again? Sorry.
So we have a lot of satellites around the Earth, which creates this space debris pollution, right?
Yes.
And now with this proposal where we are destroying near Earth, this image, and now with this proposal that you're putting forward here, that we'll have several nodes and we'll have this interplanetary network, given a lot of long distance, the scale of the distance.
Yes.
Case definitely will be putting way more satellites or these communication nodes in between. So what is
right.
it on that? Are there enabling technologies to minimize the number of nodes?
Yes, I mean, so as I mentioned, like artificial intelligence or machine learning and you know, cloud computing, edge computing, these are very critical for the future space computation. Since they're really further away, right? It takes around like 6 minutes, but of course depending on the orbit, because the orbit of the solar system already changed. So there are at least several minutes or even several hours latency for you receive and send the signals. In that scenario, you definitely need some smarter algorithm. So as I can see, machine learning has to be one of them, and the robotics from the hardware perspective very important. So it can remote operating and the response to any urgency. I mean, we can learn a lot of good lectures from like NASA's Mars missions where they send the rovers on the Mars, and basically they do the autonomous landing, deployment, spectroscopy, sensing stuff, right? So, I mean, we will depend on those technologies more and more, and that's a very promising direction for the research, I suppose. I mean, federated learning, right? I mean, pretty much like a decentralized learning, distributed learning, and we just deploy and we leave them alone. Because this robust and solid algorithm built in those space loads, they can self-optimize. They can do the best solutions and give the best decisions by themselves without the manual interference. I think less mistakes and errors could be achieved. Also, it involves very serious regulations here. We needed to build up very serious laws to supervise, to monitor, those space project by the public. Because as I research these interplanetary networks, I found out that for example, like for the neo risk deflection technologies, one of the authors, like half a century ago, mentioned they can be also used for doing something bad on the Earth, right? You can deflect them. You can also do something else on the opposite. So you have to set up very serious regulations to rule out all the bad possibilities or bad intentions. That is why artificial intelligence will be so important, because AI most of the time very neutral. If you give the proper trainings, they become very neutral. They becomes very righteous. They don't have like human emotions, which could cause some mistakes or the errors, which is not designed for the future space load deployment.
Okay, thank you. So
Thank you.
we have just one more minute, and before we move on to the next keynote, and there is a question in the Q&A. HAPS versus satellite, what is more efficient in terms of telecom? So I think high altitude platforms.
Yeah, so that's very interesting and very important question. I mean, thank you, Nasir and Puma, to bring up. So actually, we know HAP is very successful. Like for example, like Google Moon has transferred some legacy to some like NTT Docomo, and to net them to deploy something called HAPS mobile. And it's supposed to be very successful, as you can see, because it stands around like 20 kilometers, and which means less latency, right? So that's a very important and advanced advantage. But satellite give you wider coverage before you can deploy HAPs in every corner of the Earth, because satellite stands at least 20 times or even 50 times higher than the HAP, which gives some like advantage to give broad coverage and to, but I mean, HAP is also a very good solution. And we have seen a lot of efforts in the communities to make it really commercial success.
Okay. Yeah, thank you, Dr. Huo. And now we move on to